Now, move on to certain issues similar to what we discussed in the case of the continuous time Fourier transform, namely the issue of finding alternate implementations to the systems described by, in this case, difference equations, their corresponding to differential equations. In short, we want to find constant linear constant coefficient difference equations. Recall that the standard form of the linear constant coefficient nth order linear constant coefficient difference equation was the following: k equals 0 to n a k y n minus k given equal to b summation for k equals 0 to m b k x n minus k. By a series of arguments of the sort we adopted in the case of the differential equations studied for alternate implementations after the introduction of the continuous time Fourier transform, here too we will argue that with no loss of generality, we can set m equals n equals even. Thus, for example, if m equals 7, n equals 6, we set A7 equals A8 equal to 0, B8 equal to 0, and we get what we want. We get 8 as the order on both sides of this difference equation. As with the study of differential equations in the context of the continuous time Fourier transform, here too we begin by applying the DTFT to both sides of the difference equation. So, taking the DTFT of both sides and using the fact that x n minus x n minus 1 transforms to 1 minus e to the minus j omega x omega, that is the Fourier transform of the first difference. We will say that for the entire difference equation we get summation k equals 0 to m to n a k e to the minus j k omega times y omega equals summation k equals 0 to n again bk e to the minus j k omega x omega. Now invoking the convolution property, which says that x omega convolved x omega times h omega equals y omega, we can write h omega equals so we get it as a ratio of polynomials in e to the minus j omega with coefficients a k and b k, which I will briefly write as capital B e to the minus j omega divided by capital A e to the minus j omega. This is what you need. This is what you get. Now, note that for any practical system, AK and BK for k equals 0 to n are all real. We only have real coefficients. Now, when all the coefficients are real, if you look at these two polynomials b e to the minus j omega and a e to the minus j omega and examine the roots, the n roots of these two polynomials, what do we expect to find? So, the n roots of a e to the minus j omega and b of e to the minus j omega are all well, let me give them names. The n roots of a to e to the j omega, which we will call P1 on to Pn, and the n roots of b of e to the minus j omega, namely z1 to zn, are all either real or found in complex conjugate pairs. We said exactly the same thing when we were studying differential equations under the CTFT, and the reasons in both cases are also the same. It is simply that if the roots are not all real or found in complex conjugate pairs, then when you re-expand the factorized form where the roots are evident to us, it will no longer be the case that the coefficients a k and b k will be purely real as they expect to be, as they are expected to be. In short, if a k and b k have to be all real, there is no choice but for these coefficients, for these roots to be real or in complex conjugate pairs. So, writing it in factorized form, we will write as follows: h omega equals product k equals 1 to n multiplied outside by b0 by a0 1 plus zk e to the minus j omega divided by 1 plus pk e to the minus j omega. But having these factors in first order factors in the form of first order factors is not particularly convenient, because the some of the zk's and pk's, as we said, might be complex, and we do not know how to implement complex coefficients in a real world system. So, we resort to living with a second order a set of second order factors, just like again what we practiced in the context of the differential equations under the CTFT. So, we will rewrite this as follows: b0 by a0 product k equals 1 to n by 2, because now there are only n by 2 second order factors, and we will write 1 plus, I will say, b1k e to the minus j omega plus b2k e to the minus 2 j omega divided by 1 plus a1k e to the minus j omega plus a2k e to the minus 2 j omega. This is what we get. Now, unlike with the z case and the p case, which could have been complex, or rather some of which could have been complex, we are assured by the fact that the polynomial roots are in complex conjugate pairs that there exists a certain pairing of the first order factors in both a e to the minus j omega and b e to the minus j omega in which A1k, A1k, A2k, B1k, B2k will all be real. For every k going from 0 to n by 2, sorry 1 to n by 2. All right. Indeed, it is that pairing would be characterized by the fact that conjugate roots, factors containing conjugate roots would be paired together. Such a pairing would ensure that factors containing conjugate roots are paired together. If you did that, you would get this kind of decomposition into second order factors with real coefficients. So, with this formulation available, we have only a few steps to go to demonstrate two new kinds of alternate implementations. The first is a cascade form structure. This directly yields the cascade form structure H omega equals B0 by A0 pi k equals 1 to product k equals 1 to n by 2 of hk of omega, where hk of omega equals 1 plus b1k e to the minus j omega plus b2k e to the minus 2 j omega over 1 plus a1k e to the minus j omega plus a2k e to the minus 2 j omega. Now, how do we implement just this much? How do we implement hk of omega? hk of omega. Remember that these are discrete systems and there is no problem employing delay blocks. The counterpart of delay blocks in the continuous time system case was the differentiator, and we did not want to have a differentiator because of several practical reasons like its tendency to amplify noise. But here and therefore, there we had to use integrators. Here that is not an issue. So, we can easily implement hk of omega as follows. You get in the input, here we will write B2k, here we write B1k, so we add all this on this side. On this side we have minus a1k, and here we have minus a2k. This gives you hk, and h omega will then be implemented as xn going into h1 followed by h2 of omega, and finally followed by h n by 2 to get y n. This is the complete description of the cascade form implementation. There is the complete details. Now, as with the case of the continuous time Fourier transforms alternate implementations, we here also have the parallel form implementation. The parallel form implementation results from carrying out a partial fractions expansion of the polynomial rational form h omega. Fine. This is how we get the formulation required for the parallel form implementation, and it comes out as follows: h omega equals h 0 of omega, which is the quotient term, plus summation k equals 1 to n by 2 of b0k plus b1k e to the minus j omega over the same second order factor containing real coefficients found in the denominator of the cascade form, namely 1 plus a1k e to the minus j omega plus a2k e to the minus 2j omega. So, in order to carry out this kind of an implementation in parallel form, we construct each of these partial components found in the summation. There are totally n by 2 of them, and finally add it to h 0 of omega, and the whole thing will give you the complete system h omega. So, in order to implement just this one particular h k of omega, I will rewrite this as summation h 0 of omega plus summation k equals 1 to n by 2 of h k of omega. So, what form does h k of omega take? Very similar to the previous case, we can use delays instead of summers, and so you get b0k, one delay, another delay, b1k, minus a1k, and here you have minus a2k, this is hk. The overall system would be implemented by taking xn and passing it through several parallel blocks, starting with h0 of omega, h1 of omega, and so on until you have here h n by 2 of omega, and then adding all these up to get y n. This is the parallel form implementation. Again, it is worth pointing out that the parallel form implementation and the cascade form implementation differ considerably from the direct form 1 and direct form 2 implementations. They would not have been possible to conceive of unless we had a mechanism to factorize the nth order differential equation into smaller second order forms, and that became possible only by the invention in this case of the DTFT, as earlier we had said that the similar alternate implementations of the differential equations became possible only with the invention of the Fourier transform, the continuous time Fourier transform. So, in both cases these new transforms have paved the way for these new kinds of implementations. That last discussion, that last remark completes our discussion of the discrete time Fourier transform.